A digital communication system transmits bits. Therefore, the bit error rate, the probability of error at bit level, is the most important figure of merit to evaluate the performance of a digital communication system. In this video, we'll see how to calculate this bit error rate. Similarly, as for the symbol error rate, the bit error rate is obtained by averaging the conditional bit error rates, the bit error rates that we have when we transmit a given symbol. And the conditional probability of error at bit level, given that we transmit the symbol AI, is obtained by adding the product between the probability of transmitting this symbol deciding any other symbol of the constellation, AJ, times the ratio between the number of erroneous bits that we have in this decision divided by the number of bits per symbol. And the probabilities of deciding the symbol AJ when we transmit the symbol AI are obtained by integrating the conditional distribution of the observation given the transmitted symbol in the decision region of the decided symbol. Now we will apply this methodology to obtain the bit error rate for this 480 constellation. 4 symbols, coordinates, symbols that are one-dimensional, coordinates -3, -1, +1, +3. Then, if we have that all symbols are transmitted with the same probability, the decision regions are given by thresholds at -2, 0, and 2, the points in the middle between the symbols that we have in the constellation. In this case, the binary assignment follows a gray encoding. We can see that symbols at minimum distance have binary assignments that differ in a single bit, and we are going to compute the probability of error. We start with the conditional bit error rate when we transmit the first symbol, A0. When we transmit A0, a -3, the conditional observation has a Gaussian distribution with mean the transmitted symbol. In this case, the mean of the Gaussian is -3. And now the bit error rate when we transmit A0 is obtained by adding the following terms. First, the probability of transmitting the symbol and deciding A1 times the number of erroneous bits in this decision divided by 2, the number of bits per symbol, and if we transmit A0 and we receive A1, we have a single erroneous bit. We have a gray encoding. This is the closer symbol in the constellation, and this is just an erroneous bit in 2 transmitted bits. This is important because clearly in the figure the probability of error corresponds to the red area, and this is the biggest probability of error with respect to any other symbol, higher than the probability of deciding A2 and higher than the probability of deciding A3 in green and cyan respectively in the figure. Then we have the probability of transmitting A0 and deciding A2, and if we transmit A0 we have 0, 1. If we decide A2 we decide 1, 0 times the number of erroneous bits, 2 in this case, divided by the assigned bits for a symbol, 2. And finally we have the probability of deciding A3 when A0 is transmitted times the number of errors that we have in this decision divided by the total number of bits. If we transmitted A0, the information bits were 0, 1. If we decide A3, the information bits are 1, 1. Therefore, we have an erroneous bit over 2 bits in this term here. These 3 symbol error probabilities can be obtained easily with the Q function and corresponds to the red area, green area, and cyan area in this picture over here. And the same procedure is repeated for the remaining conditional probabilities of error. The conditional bit error rates for A1, the difference is that now the conditional distribution of the observation is a Gaussian with mean -1, the value of A1, and now we need to multiply the probability of transmitting A1 and deciding A0 times the number of errors that we have in this decision, 1 out of 2 bits, the probability of deciding A2 times the number of erroneous bits in this situation, again 1 out of 2 because A2 and A0 are the symbols that are closer to A1. Therefore, gray encoding differs in a single bit for the binary assignments of A1 with respect to the binary assignments of A0 and A2. And then we have the probability of deciding A3 with the number of errors that we have in this situation, 2 divided by n. And we can repeat this process equivalently for the conditional distribution. Given A2, now the Gaussian is centered at 1, the third symbol, and finally the same thing can be repeated for the last symbol. Now the conditional distribution of the observation is a Gaussian centered at 3, which is the last symbol A3. Once that we have the conditional bit error rates, they are averaged to obtain the bit error rate. If the binary assignment is modified, and for instance, in this binary assignment, we don't have a gray encoding, because for instance, these symbols are at minimum distance and they differ in 2 bits, the BER, the bit error rate will be modified, because in the previous examples, if we now modify the binary assignment, these probabilities of symbol errors will not change, but these terms here will change. And in this case, the higher probabilities of error at symbol level, in some cases, will not have the term 1/2, but the term 2 divided by 2 equal to 1. And because of this bit error rate is higher than this one. We can see that the dominant term is this one, and here we have 3/4, and here we have 5/4.